Hi everyone! Today let's talk about section 1.2 and 1.4, separable equations and applications. Given the first order ODE, dy dx equals f of xy and the initial condition y of x0 equals y0. So we can make a direction field to obtain a qualitative picture of the solution. So we can estimate what the graph of the solution look like. And we also learn about how to use the theorem of existence and uniqueness to show whether a solution is guaranteed to exist or whether it's unique. Okay? Next, we're going to talk about the analytical solutions for the differential equations. How can we actually solve the differential equations and get a formula for y of x? And just like calculus 2, there are a lot of antiderivatives that we're not able to get. Similarly, for the differential equations, there are a lot of differential equations we're not able to solve and get a nice formula. So in our course, we're going to talk about the following cases where we can solve the differential equations. Okay, so the first one, dy dx is f of x. So this is just a function of x. Well, then we just integrate both sides. Okay, so this is like a subset of linear ODE we're going to talk about today. And then for the, in general, linear first order ODE, we're going to talk about in session 1.5. And then the next one, separable ODE, you can see the left hand side, we can move all the y to the left hand side and all the x to the right hand side. So this is a separable ODE, and usually it's nonlinear in general. And we are going to talk about that today. And then the next one, dy dx equals f of y. So this is a function of y only. Okay, so this is autonomous differential equation, is like a subset of separable differential equations. And we're going to talk about that in session 2.1. Okay, so here are the types of differential equations we're going to cover. Alright, so let's talk about the first one, dy dx equals f of x. Well, solution by direct integration. So y of x is integral f of x dx plus c, where the integral f of x dx is the antiderivative of f of x. And then to find c, we just plug in the initial conditions. So this is the formula we can get. Okay, and here you need to review techniques of integrations in calculus 2, like the U substitution, integration by parts, partial fraction, trig integrals, trig substitutions, etc. Okay, next, separable differential equations means we can move all the y to the left hand side and we can move all the x to the right hand side, and then we can integrate both sides respectively. Okay, and then we can get something like this, and we can also plug in the initial conditions to solve for c. Okay, so let's work on some examples. So example 1, y prime equals y squared, y of 0 equals 2. Okay, so let's see, dy dx equals y squared. So we want to move all the y to the left. When we say move, we mean divide or multiply. So don't subtract, okay? So here we should divide it by y squared. And we have dy over y squared. And we also want to multiply by dx. Okay? Alright. And then what is next? Okay, so the left hand side is like y to the minus 2 dy. Now we can integrate both sides. Let me remind you, integral of x to the p dx is x to the p plus 1 over p plus 1 plus c. Integral of 1 over x dx is ln of absolute value of x plus c. Okay, now y to the negative 2, what do? We put y to the negative 1 over negative 1, right? And integral of 1 is x. So x plus c. And then next, if we're able to solve for y, please solve for y explicitly. Okay, and let's see. So we have like both sides multiplied by minus 1. We get 1 over y equals minus x minus c. But we can like change it to be d. Okay, and then the y is, we flip it over, so minus x plus d. And then next, we want to plug in the initial conditions. Alright, let's see. Okay, let's plug in y of 0 equals 2 inside here. So y plug in 2, so 1/2 equals x is 0. And then, so we get d equals 1/2, right? So then we can plug in, we get minus x plus d, d is 1/2. Alright. Sometimes if we don't want to see fraction in the fractions, we can multiply the numerator and the denominator by 2. And then so we have 2 all over, we can flip this, 2 times 2 is 1 minus 2x. Okay, so this is the solution. Alright, let's continue. Y prime equals xy squared e to the x. And you can see because it's y squared, so we know this is nonlinear and it is separable. Right? Separable is, it means the right hand side you can see, you can separate. This is like a product of functions of x and function of y. So you can separate them. Okay? And let's look at this guy. By theorem of existence and uniqueness, we can see x0 is 1, y0 is 0, and the right hand side is xy squared e to the x. Partial f partial y is 2xy e to the x. Because they're both continuous everywhere, so we know a unique solution exists, right? Okay, so let's see. We can move the y squared to the left, so we have dy over y squared. On the right hand side, we have x e to the x dx. Okay, so remember, first steps, you want to have your left hand side is y prime, and then your right hand side you want to separate them as like a product, a function of x and a function of y, and then you want to divide g of y to the left, and then f of x dx on the right, and then you can both sides integrate. Okay, so now let's see. On the left, we know this is like integral y to the minus 2 dy. On the right, x e to the x. Okay, so I need to recall your memory. Okay, if we see x times e to the x, what method do we use? Okay. So let me ask you, okay, if you see e to the kx dx, so this is e to the kx divided by k, because when you take the derivative, you multiply by k, so then you take the antiderivative, you will divide it by k. And then if you have like x e to the kx, or it's like x to the p e to the kx, you use integration by part. Okay, and you let u be the polynomial or power function, and then the rest to be dv. Because the integration by part formula is u dv equals uv minus integral v du, so you're going to differentiate the u and integrate the dv. And you can see if we let u to be this polynomial, when we take the derivative, the degree will go down by 1, so the problem is easier in that case. And if you see x e to the x squared dx, what method do you use? U substitution, because you let this guy be u, and then du will be 2x dx, then you can use u substitution to solve it. Okay, so all this antiderivative formula and integration techniques from Calculus 2, please review those, because we're gonna need it in our course. Okay, so on my website, you can also find my Calculus 2 course. So you can go there and then look at the notes and lecture videos to review. Okay, if you have questions, feel free to ask me. Okay. All right, let's continue. So integral y to the -2 is minus y to the -1, and then the right hand side is integration by parts. So u is x, dv is e to the x dx, then du is dx, v is integral of e to the x is still e to the x. Okay, then we get uv minus integral of v du. Alright, then x e to the x, integral of e to the x is e to the x plus c, okay? So don't forget the plus c, okay? And let's see what happened. So what is, we multiply both sides by -1. We get 1 over y equals minus x e to the x plus e to the x minus c, but we can rename to be a new constant. And so for y, we get minus x e to the x, e to the x, and d. Okay, we have initial condition y of 1 equals 0. So we plug in x is 1, and then the y we get is 0. Let's plug in here. It's easier to plug in here. Oops. Let's see. Oh, what happened? Can you see, because y is in the denominator, okay? Because y is in the denominator, can't plug in 0. Okay? So now what happened? Okay. So here, actually, what happened is at the beginning, when you divide it by y squared, you are assuming y is not 0. But actually, y equals 0 is the solution. Why? Okay, let me copy down the differential equation. Y prime equals x, y squared e to the x, right? Okay, consider the solution y equals to 0. Sometimes people use this notation. This notation means constantly equal to 0. So then this is what? The x-axis, right? Y equal to 0 is the x-axis. And then y prime is also 0, so then you can plug in, you can see y prime equals y. So y equals to 0 is a solution. Alright, so that's why here, because our initial condition y of 1 equals 0, so the y is 0, so that's why the solution is, so, okay, because initial condition is 1, 0, so the solution is y equals 0. Okay, then you might ask, oh, how about this? Well, so this, okay, so consider the slope here, right? I don't know the slope here, what it looks like. but we know, okay, maybe we have some other picture like this. I'm not quite sure, so just write it down, okay? Alright, so with the other initial points, then we will get the formula. This guy is the formula, okay? But if the initial point is on the x-axis, then the solution in y is 0. Okay, last time, do you remember that for nonlinear differential equations, then the solutions, you might expect to see a general solution where you get a formula and a lot of functions look like this form, and some particular solutions that it's not in the form of the general solutions. So those solutions are the singular solutions. So you can see here, these are the singular solutions. And these are the general solution. Okay, so the general solution for the nonlinear differential equations does not contain all the solutions. Okay, so there could be some exceptional case that you don't have the same formula. So for example, in this case, y equal to 0 is that exceptional case. It is a singular solution. Alright. So let's continue. And let's see here. Oh, here. Similarly, if y of 0 equal to 0, then you will, okay, so let me put a remark here. If the initial condition is 0, 0, then the solution is y equals 0. Okay, so similarly. Alright. Let's continue. Example 3. Oh, example 3. Do you see now is the same differential equations but with a different initial value, okay? Now we can then plug in this formula and figure out what is the d. Okay, so 1 over y equals minus x e to the x plus e to the x plus d. Plug in x is 1 and y is 2. Then we have 1/2 equals x is 1, so minus e plus d. So d is 1/2. So finally, y is what? Remember, it's this guy, and you plug in d equals 1/2. So minus x e to the x plus e to the x plus 1/2. Oh, and actually this guy is it's like when x goes to infinity, the denominator is getting bigger. So you kind of know the picture will be, let's see, will be something like this. Okay. All right. Let's continue. Note. Okay. So let's just write down what I said before. Note y equals the 1 over minus e to the x e to the x plus e to the x plus d. This guy. And y equal to 0 are solutions to the differential equation. And because the differential equation is nonlinear, that's why we have the general solution. But general solutions don't include all the solutions in this case. And we also have a singular solution. Alright. And we know if the differential equation is linear, then the general solutions include all the solutions. So all the solutions must be in this form. Okay? So if a differential equation is linear, then the General solutions include all the solutions. Okay. Maybe I said this. Okay. Alright, let's do more examples. Example 4, look at the following. Alright, y prime equals y squared e to the x plus e to the x. Well, this is a sum. This is not a product. But the first thing you think, is it possible to express this guy as a product of a function of x and a function of y? Well, in this case, yes, you can factor out e to the x, then we have y squared plus 1. Alright, so what is this? We can both sides divide it by y squared plus 1 and multiply by dx. Okay, on the left, what is that? Okay, let me remind you the formula for the antiderivative of the inverse trig functions. So let's see. Oops. Alright. So integral of 1 over x squared plus a squared dx. This is 1 over a tangent of x over a plus c. Integral of 1 over square root of a squared minus x squared dx is sine of x over a plus c. Okay, so keep this in mind. Then on the left, you know, our variable is y, our a is like 1, so this is just tangent of y. The right hand side, e to the x antiderivative is e to the x plus c. Okay, now let's plug in. Y of 0 equals 1. So tangent of 1 is e to the 0 plus c. Okay, what is tangent of 1? Well, you draw the picture of the graph of tangent. So this is tangent of x, right? This guy is pi over 2. This is minus pi over 2. So the x of the tangent corresponds to the y of the tangent. So if the y is 1, what is the corresponding x? Pi over 4. So this is pi over 4. Now c is pi over 4 minus 1. So that's why tangent of y is e to the x plus pi over 4 minus 1. Oh, we can actually solve for y. We can apply tangent on both sides, right? Then tangent and arctangent cancel. Then we have tangent e to the x plus pi over 4 minus 1 on the right hand side. So far, so good, everyone. So sometimes if you are able to solve a y, please do it. Alright, let's continue. Here we have y double prime 1 over x squared plus x plus 1 cubed. Okay, so this is a second derivative. What do we do? Well, let's see. So we have, this is the same as d of dy dx, right? Okay, so first we want to integrate it one time. Alright, so if we integrate this guy one time, we will get dy dx. Okay, so what is this? Well, here we're doing u substitution, right? We let u be x plus 1, and then du is dx. But then this guy is integral of du over u cubed, right? So this is like u to the minus 3 du. So integral is u to the minus 2 over minus 2, right? Plus c. And what is that? Well, u is x plus 1. So x1 is 1 over 2 times x plus 1 squared plus c. Okay, so this is y prime. And we can figure out c by plugging the initial condition y of 0, 0. So when we plug in that, we get 0 equals, if we plug in x is 0, we get 1 half. Alright, so c is 1 half. So then dy dx is minus 1 over 2 x plus 1 squared, and then c is 1 half. Okay, then we continue, integrate one more time. Then we can separate them, right? We can separate them and we get, let me rewrite it. This guy, we can do u substitution, and integral of 1 half is 1 half x. Alright, now let's see. Here, the similar things, let u be x plus 1, then du is dx. So integral of u to the minus 1 half is u to the minus 1 over minus 1 plus 1 half x plus c. And then you can see minus cancel. And this is just 2 times x plus 1 and plus 1 over x, 1 over 2x plus, let's call it d because we already have c on top. Let's call it a different name. Okay, now let's plug in y of 0, 0. So 0 equals 1 half plus 0 plus d. Oh, d is also 1 half. Sorry, minus 1 half actually. Okay, now y is finally 1 over 2 x plus 1 plus 1 half x minus 1 half. So this is the solution. Alright. Let's continue in the next video. See you soon.